Okay, so in this video we want to prove that there are infinitely many primes that are 3 more than a multiple of 4. Remember, Euclid's algorithm tells us that there are infinitely many primes, and the way he did it was he supposed, for contradiction, suppose there are only finitely many primes. Well then, you can make a list of those primes, p1, all the way up to pn, and you can multiply them together and add 1. This gives us a number, and this number we know must be composite because we've made a list of all the primes, and this is bigger than all of them. By the fundamental theorem of arithmetic, it has prime factors. We'll pick one, let's call it pi, and then we know pi divides this. But pi, it divides this product because it's a product of all the primes. So this pi is somewhere in here, so pi divides this product. If pi divides the sum, and it divides one of the terms in the sum, then it divides whatever is remaining, which is this 1. So that means pi divides 1. But there is no prime that divides 1. This gives a contradiction. And so this is Euclid's argument that it cannot list all the primes. And so there must be infinitely many. So we want to use a similar idea to show that there are infinitely many primes that are 3 more than a multiple of 4. So first of all, what we want to do, and this is going to be a homework, is to show that if m and n are 1 more than a multiple of 4, so let's say m comma n is congruent to 1 mod 4, or we can say we can find some numbers a and b so that you can write it like this. So it's 4a plus 1 or 4b plus 1. Well, I want you to check as homework that the product, this product, is also congruent to 1 mod 4. This is not difficult to show. If you know modular arithmetic, you can just do 1 times 1. Otherwise, you can try and multiply these two together, and you can see if you can get that mn is 4 times something, let's call it c, plus 1. Some integer c, which will be in terms of a and b. How is that useful? Well, what that means is, if we have a number, that number is 3 more than a multiple of 4, well, we can prime factorize it. So let's suppose we have a number that's 3 more than a multiple of 4. Then we can prime factorize it. Let's call it p1 dot dot to pn. Well, we know that none of these primes are even. There's only one even prime, which is 2, but if 2 was a factor, then 2 would divide this, but this is clearly odd. So none of these primes are 2, and so all the primes are odd. That means the primes are either 1 more than a multiple of 4 or 3 more than a multiple of 4. If they were all 1 more than a multiple of 4, we know if we multiply together numbers that are 1 more than a multiple of 4, then it gives another number that's 1 more than a multiple of 4. So it wouldn't give us a number that's 3 more than a multiple of 4. So at least one of these primes, the key idea is at least 1 pi is congruent to 3 mod 4. Okay, so why is this important? Well, let's suppose that there are only finitely many primes that are 3 more than multiple of 4. That means, just like before, we can make a list of them, pn like this. All of these are 3 more than multiple of 4, and we can take a product of them. This time, unlike Euclid's argument where we added 1, we're going to do this conditionally. When we take a product of this kind, the result will be an odd number, because we're multiplying two odd numbers, and odd numbers are either 1 more than a multiple of 4 or 3 more than a multiple of 4. So in the first case, I suppose it's 1 more than a multiple of 4, which is going to be kind of a little bit easier. In the case that this is 1 more than a multiple of 4, that is, if it's congruent to 1 mod 4, put this in brackets, then what we want to do is we want to add 2 to it. When we add 2 to it, this is going to be congruent to 3 mod 4. And using our argument from before, if a number is congruent to 3 mod 4, then at least one of its prime factors is going to be 3 mod 4. And that means one of these pi's will be the prime factor of this number. So we have pi dividing this. And so then this implies that pi, well, because it clearly divides this, so it must divide the 2 as well. So it divides 2, which is a very similar kind of argument we made up here with Euclid's argument. But pi, in this case, there is no prime that's 3 mod 4 that divides 2. And so this gives us a contradiction. In the case that the product of all the primes that are 3 mod 4 is 1 modulo 4, then we have a contradiction. We've shown it's not possible for the product of all prime numbers that are 3 more than a multiple of 4 to be 1 modulo 4. Assuming that the product exists, we've shown that the product can't be 1 more than a multiple of 4. So to conclude the proof, we want to show that it also can't be 3 more than a multiple of 4. If we've shown it can't be 1 more than a multiple of 4 or 3 more than a multiple of 4, then it can't be anything, right? Because it's an odd number, so it must be either one or the other. And if we've shown it can't be either one, then our assumption that the number of prime numbers that are 3 more than multiple of 4 is finite will be wrong, and then that means there must be infinitely many primes that are 3 more than multiple of 4. So let's take the other case. In the case that the product of all the primes that are 3 more than multiple of 4 is congruent to 3 mod 4. In this case, we're going to add 4. Okay, well, if we add 4, then it will still be 3 modulo 4, because we could just, the modulo 4 would cancel out the 4, or make it the 4 equivalent to 0. And so again, this is congruent to 3 mod 4. In this case, because it's 3 mod 4, by argument from before, any number that's 3 mod 4 will have a prime factor that's 3 mod 4. So it's divisible by some prime, pi, and that's 3 mod 4. Okay, well, what does that mean? Well, that prime number is in our list because we took the product of all numbers that are 3 mod 4. And so then it divides this. And because the entire sum divides this, one part of it divides it, then the remaining part must also divide this prime. So that means pi divides 4. But there is no prime that's 3 more than multiple of 4 that divides 4. And so this gives us contradiction. That means this product cannot be 3 more than multiple of 4 or 1 more than multiple of 4. And that actually means it can't even be odd, because that's the only possibilities for a number being odd. And we know that product, if it is finite, must give us an odd number, which gives us a contradiction. So I hope that made sense. Thanks for watching.